On this lesson, we will talk about the area and volume of similar solids, and then we're going to talk about the scaling principle. So let's get started. So let's start by looking at the introduction question, which states, let's take in consideration the following pair of right cylinders and right square pyramids. So here we have our right cylinder, and here we have our regular square pyramid. And the first thing we want to do is we want to determine whether the bases are similar, and then we want to determine if the corresponding legs are proportional. So let's take a look at just this right cylinder first. First, we want to determine whether the bases are similar. Well, in a right cylinder or in any cylinder, the bases are always going to be a circle. So notice that the base of the first figure, it's a circle. The base of the second figure, it's a circle. And one thing that we know is that all circles are always going to be similar. So therefore, yes, the bases are similar. The bases are similar since all circles are similar. And the circle is what we have as a base. So that takes care of letter A. Now we want to determine if the corresponding legs are proportional. So let's take a look at B here now. So what do we mean by corresponding legs? Well, we want to compare the radius of the first figure with the radius of the second figure. And let's see if there's any proportionality between them two. Also, when we take a look at the heights as well. So how do we do that? Well, let's take a look at the radius of figure 1, and let's divide it by the radius of the second figure. And if we simplify this, this becomes 3 halves. Now, let's take a look at the height of the first figure. And let's divide it by the height of the second figure. But notice that we also get the same value, 3 halves. Now, notice that what we have done here, we have found some kind of proportionality. Since the proportionality among the radius and the proportionality among the heights are the same, 3 over halves, and since they have a similar base, then with those two ideas together, we can make the claim that we have similar solids. So we can say that figure 1 and figure 2 are two similar solids. Why is that? Well, we can see that the bases are similar. And in addition of that, we have also seen that the sides and even the radius of those figures, they are in proportion. When we take a look at 6 over 4, that was the same value as dividing 12 over 8. And we would have the same if we would divide any other proportionality or any other lengths among these two right cylinders. So now let's see if we can do the same for the regular square pyramid. Let's start by determine whether the bases are similar. Well, the base for this regular square pyramid is a square, and also the base for the second regular square pyramid, it's a square. So in that case, yes, bases are similar because or since all squares are similar. So now we can determine that yes, the bases are similar. Now, let's see if we do have this idea of proportionality. Well, let's take a look at the height of the left regular square pyramid, which is 8. And let's divide it by the height of the second square pyramid, which is 4. Well, this gives us a value of 2. When I take a look at the slant height of the figure on the left, and let's divide it by the slant height of the figure on the right, that is 2 as well. Well, let's take a look at this side of the regular square pyramid, which is 12. And let's divide it by the same side of the second figure, which is 6, which is also 2. But notice that the lengths of those two regular square pyramids are also in proportional. There's a proportionality among the lengths that determine the regular square pyramid. Since they have similar bases and the sides are in proportion, then we can say that these two solids are similar solids. And this is exactly what we're going to be discussing today. What properties come from the idea of having similar solids? And one thing that I would like to point out before we move forward is the idea of a scale factor. Well, the scale factor is going to be the value which the lengths are in proportion of. So notice that here the radius, we're in a proportion of 3 over 2, 12 over 8. It's also determined by 3 over 2. So we can make the claim that there's a scale factor of 3. Oops, that's an ugly 3. So 3 over 2. And the same idea here. Notice that these figures also have a scale factor. And the scale factor is the proportion among the lengths of these figures. And notice that when we divided the height, we got a value of 2. When we divided the slant heights, we also got a value of 2. And the same goes with the side of the bases. So we can make the claim that the scale factor is of 2. So what we're saying here is that, well, what I mean by scale factor 2, we also have to take in consideration the direction. So I guess for here, our direction is here. So any length that we got on the smaller triangle, if we multiply it by 2, we're going to get the same value, or we're going to get the value of the same length on the second figure, since there are similar polygons. And the same idea here. I guess the direction is from left to right. If we take 8 and we multiply by 3 over 2, we should get 12, because that is the proportion that they share. If we get 4 and we multiply by 3 over 2, we should get 6, because that's the proportion that we obtained when we were measuring, when we were comparing the lengths of those figures. So this is an introduction about what is a similar solid. Similar solids are going to be those solids which have similar bases, and also their sides or the lengths are in proportion. And let's just give a small definition for what similar solids are. And we can kind of think about solids or similar solids as being solids that have the same shape, but not necessarily the same size. And to properly call two solids to be similar, we have to take a look at the length. So the length of solids must have the same scale factor, or must have the same scale, which is exactly what we found out with those two figures. In this case, the scale factor was 3/2, because that's how we determine by dividing the same lengths of two solids, and the same goes with regular square pyramids. So why are we talking about similar solids? Because now we can talk about the scaling principle. And again, the scaling principle, it's only applicable to similar solids. So now that we have discussed what a similar solid is, let's take a look at some ideas here. In this small exploration activity, we want to take in consideration the pair of right cylinders, which we discussed on the introduction question, and we want to compute the following. So we're going to take a look at A first, and under A, we want to compute the base perimeter of figure 1, and we want to compute the base perimeter of figure 2. Then we're going to divide their perimeters, and we're going to notice something. So let's start by that. So let's take a look at the perimeter for the base of figure A, or figure 1. So here we have figure 1, and again, it's a perimeter. And to find the perimeter of a circle, we know that we can find that by, well, for the perimeter is 2 pi r. So therefore the perimeter of my first figure, notice that our radius is 6, so we're going to get 2 pi times 6, which is equivalent to just 12 pi. Now let's find the perimeter of the second figure. Now for the second figure, the radius is 4, so our perimeter is going to be 2 pi times 4, which is 8 pi. So now that we have computed the perimeters, let's divide them. So let's take a look at the perimeter of the first. It's 12 pi, and let's divide it by the perimeter of the second, which is 8 pi. Well, in this case, the pi's will cancel out. And now we get 12 over 8, which this can be reduced to 3 halves. Okay, let's continue working on this, and then let's just make a small observation at the end. So now that we have found the division among the perimeter of both figures, now let's take a look at the lateral area of the first figure. So the lateral area of the first figure, well, remember that for the lateral area, we have 2 pi r times the height. So for the lateral area of the first figure, we're going to get 2 pi times 6 times the height, which is in this case going to be 12, which this can be reduced to just 144 pi. And for the lateral area of the second figure, we're going to get 2 pi times the radius of the second figure, which is 4, times the height of the second figure, which is 8, which is equivalent to 64 pi. And since we're talking about lateral area, so let's just assume that this is unit square, just to keep the same units. Now let's find the division of those two. So if I take the lateral area of the first, which is 144 pi unit square, over the area of the second, 64 pi. Now notice that this is equivalent. Well, here we can see that the pi's are going to cancel out. So now this just reduced to 144 over 64, which is equivalent to 9 over 4, which this is equivalent to 3 halves square. We're going to come back to the observation at the end. Now, let's take a look at the bases. Let's take a look at the volume. So if we find the volume of the first figure, well, recall that the volume for a right cylinder is going to be equivalent to pi r squared times the height. So if we want to find the volume of the first figure, we're going to have pi, the radius of the first figure, which is 6 squared, times the height, where the height is 12, which this is going to be equivalent to 432 pi. It's units cubed, since we're talking about volume. And now, if we want to find the volume of the second figure, that's going to be pi, the radius of the second figure, which is 4 squared, times the height, which is 8, which is going to be equivalent to 128 pi. Units cubed. So now, let's divide the volume. So if we take a look at the volume of the first figure, so 432 pi, I'm going to leave the units cubed because they're going to cancel out. And if I divide it by 128 pi, well, the first thing that we're going to notice is that the pi's are going to cancel out. And now we're going to end up with 432 over 128, which reduces to 27 over 8, which this can be rewritten as 3 halves to the third. So now that we have computed the perimeter, the lateral area, and the volume, now let's take a look at the conclusions that we got here. So I know that at least if I divide the perimeters, I want to get a value of 3 halves. Now, if I divide the lateral areas, I want to get a value of 3 halves square. And if I divide the volumes, I want to get a value of 3 halves cube. So what seems to be the relationship among the two? Well, notice that 3 halves was the scale factor that we got when we were taking a look at the sides or the lengths of these similar right figures. So when we divide the perimeters, we're gonna get the scale factor. So if we divide the perimeter of one similar polygon with the perimeter of the second similar polygon, we're always gonna get the scale factor. And if we divide the lateral areas, we're always gonna get the scale factor to the second. And if we would divide the volumes, we're always gonna get the scale factor to the third. And we can use this relationship now to compute or even solve some word problems, which we're going to take a look in a couple of minutes. But this is the idea here. This is what we call the scaling principle. The scaling principle is that if we find the proportions among the perimeters, it's always going to be equivalent to the scale factor. If we find the proportions among the lateral areas, we're always going to get the scale factor twice, or a scale factor square. And we find the proportions among the volumes, we're always going to get the scale factor to the third. So let's just generalize this. So if we want to generalize our results, then let's assume that the scale factor of the two similar solids is a ratio of A over B. Then the ratio of the corresponding perimeters, that is still A over B, because that's what we got here. The scale factor was 3/2, so therefore, when we divide the perimeters, it is still 3/2. Now, the ratio of the basis areas, of the lateral areas, and the surface areas, now it's going to be equivalent to A squared with B squared. So what are we saying here? Well, if my scale factor is 3/2, then the proportions among the lateral areas is 3/2 squared. So therefore, at least in this generalization, if we're saying that the scale factor has a ratio of A over B, then the ratio among the surface areas A squared with B squared. And for the volumes, that's going to be A cubed over B cubed. Well, not over, but just proportion with B cubed. And this is what we call the scaling principle. And this is very important. This is only true with solids that are similar. If you are working with solids that are not similar, then the scaling principle cannot be applied. The scaling principle only applies if we have similar polygons, because if we have similar polygons, then we can determine a scale factor. If they're not similar, there's no scale factor, so there's no proportion. Now let's take a look at how we can use this information. Well, first, let's start by looking at the following figures, and let's see if we can decide if those similars are similar, if the solids are similar. So let's take a look at A. So how do we determine if the solids are similar? Well, let's take a look at the heights and let's divide them to see what factor we get here. Well, 12 over 8, that's equivalent to 3/2. And now let's take a look at 3 over 6. Now this is equivalent to just 2. Now, notice that we don't have the same value here. So therefore, these two figures, or two solids, are not similar. They're not similar because when we compare the radius with the radius and the height with the height, we didn't get the same value out. So therefore, there is no scale factor. And if there's no scale factor, so therefore, the solids are not similar. Now, under example B, let's see if these two figures are solids. Well, I'm going to assume that, at least in here, I took in consideration that we already know that the bases are similar because they're both circles. Here, triangles are similar, so that's fine. Or right triangles are similar. So now let's take a look at the lengths. So let's compare the height with the height. So let's do 12 over 8. And what does this give me? That gives me 3 over halves, or 3/2. Now let's take a look at the left-hand side with the left-hand side. 9 over 6. Well, this is still equivalent to 3 halves, so very good. So we already compared these two sides with these two sides. Now let's take a look at the next ones. 12 over 8. I want to compare in this right-hand side with this right-hand side. Well, 12 over 8. This is still computed as 3 halves, so that's good. So the only thing that we need to compare now is, I don't know if you can barely see it, but that's a 15 and that's a 10. So let's see, we still got the same value, 15 over 12. Oh, sorry, we said that was a 10, not a 12. It's still equivalent to 3 halves. So notice that we found the relationship among the sides. So if we would divide the height with the height, the left with the left, the right with the right, the base of this triangle with the base of this triangle, we always get the same value out. So therefore, all sides are in proportion. And this is enough in order for us to make the claim that we have similar polygons. So this is how we can determine if we have similar polygons. Well, first take a look at the bases. If they seem to have the same base, then you're good. Now, what you need to do after that, you need to find the proportion among the sides of those polygons, or not polygons, but solids. Now, let's take a look at the last example for this lesson. And this example is a little bit conceptual, so we're going to take a little bit slow here. So let's understand the question before we actually go and start working on it. So we have a plane, which is PQR. So here we have a plane PQR, which notice that it kind of creates a triangle here, which is parallel to the base of the pyramid. And the base of the pyramid is another triangle, ABC. And it bisects the altitude. So this PQR is going to bisect the altitude of the solid. And what we want to do is we want to find the following ratios. Let's start by finding the perimeter of triangle PQR. So here we have triangle PQR with the perimeter of triangle ABC. Well, since PQR is parallel and to the base of the pyramid, and to the base of the pyramid, and it bisects the altitude of the whole pyramid, then we can assume that this solid, the solid PQR, which is a triangle, and the solid ABC, which is the bigger triangle, they're both going to be similar. So now that we know that they're both similar, what we can do, we can start applying the scaling principle. And the scaling principle says that if the scale among, or not just the scale, but the scale factor. So remember that the scaling principle says, well, if the scale factor of two similar solids is A to B, then the perimeter, it is still A to B. The lateral area is A squared to B squared, and the volume, is A cube to B cube. So we're going to be using our scaling principle, and this is what we observe on the introduction question here. So now, if we want to find the perimeter of triangle PQR to the perimeter of triangle ABC, we want to find the ratio of those two. Well, notice, since we already said that those two solids are similar to each other, therefore, we can still use the scaling principle, and the perimeter are still going to have the same scaling factor, A to B. Well, in this case, the scale factor is going to be 1 to 2. And why is it that the scale factor between those two is 1 to 2? Because in here, it states that the pyramid on the top is going to bisect the altitude of the overall triangle. So therefore, it's kind of like half of it. So half over 2. So we know that the scale factor must be 1 to 2. Well, if the scale factor among these two solids, and let me identify those two solids, So we're talking about this solid right here, and we're talking about this other solid right here. They have a scale factor 1 to 2. So whatever we have here as 1, the blue is going to be double than that. Well, if the scale factor is 1 to 2, and the scaling principle is telling me that the perimeter, it is still 1 to 2, or still A to B, so now we can make the claim that for the perimeter, still has a proportion of 1 to 2, because that's what the scaling principle is telling us. So that takes care of A. Now for B, it says the lateral area of the top part of the pyramid to the lateral area of the whole pyramid. Well, since those two solids are similar to each other, we know that the lateral area must follow a scale of a squared and a squared to b squared. So therefore the scale factor is 1 to 2 for the lateral area. It must be 1 square to 2 square. And what do we get from that? Well, this is just 1 to 4. So now we know that the ratio among the lateral areas of the upper triangle or the upper solid to the lower solid is going to be 1 to 4. So that takes care of B. So now for C, let's take a look at C over here. So that takes care of A. That takes care of B. So now for C, it says we want to find the lateral area of the top part to the pyramid to the lateral area of the bottom part. Now we gotta be a little bit careful here, because here, the way that this problem is stated, it says the lateral area of the top part of the pyramid to the lateral area of the bottom part. So this is what we refer to as the top part. So here we have the big pyramid right here. So this is the top part. And now what they refer to as the bottom part is this whole figure right here, or this whole section of the pyramid. So this is the bottom. So now we want to find the ratios. We want to find the ratio of the lateral area of the top part to the pyramid to the lateral area of the bottom part. Well, for the top part, we already found that. The top part was a lateral area of 1, because that's what we know, that it has a scale factor of 1 to 4. So if the scale factor was 1 to 2, the lateral area is 1 square to 2 square, so therefore it's 1 to 4. So the top is going to have a unit of 1, and now the bottom is going to be a little bit tricky, because now the bottom is just this section right here. This section right here. Well, I know that the lateral area of the upper pyramid, it's of 1, and the lateral area of the whole pyramid, it's 4. So therefore, the bottom section is going to be 4 minus 1. I know the whole thing is 4, or has 4 units, and I know that the upper section right here, it's of 1 unit, so therefore this section right here is the whole minus the upper, or the top, which is 4 minus 1, which is just 3. So therefore the ratio that we have among the top part of the pyramid, the lateral area, to the bottom part is just going to be 1 to 3. And now for D, we want to find the ratio of the volume of the top part of the pyramid to the volume of the bottom part. But notice that we have not said anything about volume. So let's find the scale, or at least the ratio of volumes. Well, we know that the scaling principle says that if they have the same scale, A to B, then the volume is going to be A cubed to B cubed. So therefore, we're going to have a ratio of 1 cube So whatever the unit is for the top, that's going to have a ratio of just 2 cubed, which is equivalent to 1 to 8. So if the area of the upper pyramid it's of a unit of 1, then then the volume, we're talking about volume, sorry. So if the volume of the upper pyramid it's a value of 1, then the volume of the whole pyramid is going to be equal to 8. So now that we have those values, now let's try to find the ratio of the volume of the top part. So for the top, again, it's going to be the upper pyramid. So we know that that has a unit of 1. Now for the bottom, we're going to apply the same idea. Well, this bottom section is going to be the whole pyramid minus the upper pyramid, where we know that the whole pyramid has a value of 8 and the upper pyramid has a value of 1. So therefore, the bottom is going to be 8 minus 1, which is just 7. So therefore, the ratio that we were looking for, so therefore the ratio of the volume of the top part of the pyramid to the volume of the bottom part of the pyramid is going to be 1 to 7. And notice how important it is to know this idea here, because we couldn't find the volume of this pyramid because all we know it was this information. We only know that we were talking about a pyramid which plane bisects the altitude. We don't know anything else. So once we know some kind of a scale factor, once you know the scale factor of two similar solids, then you can find the proportion among the perimeters, you can find the proportion among the lateral areas, and you can find the proportion among the volumes. And this is due to the fact that the scale principle it is present in all solid or solid similar solids. And with this, it concludes our lesson for area and volume of similar solids with an emphasis on the scaling principle.